imagine that I ask you to play the role of a football manager, and I tell you that you have 4 types of players. Each one of them scores a different number of goals per game. And I train you on these numbers, so you know them well. And then I show you this team, and I ask you how many goals do you think this team is going to score as a whole. So there are different ways you can go about solving this problem. One way, for example, is to just get an impression of the team as a whole. Say, okay, there are around 7 players here. Each player scores. We know that on average, player scores a little bit less than 1 goal per game. So probably it's going to be something like 6 goals. And so this is one way where you take in all the information at the same time. The other way is that you can think about each player type in turn. So you start from the player that scores the most goals. You say, I have one player that scores 1.6 goals. Then you add up the second player. You have 3 of these, and each of these scores 1.2 goals. And you do the calculation essentially serially, right? So this serial strategy is more precise, but it can also take more time. And importantly, it doesn't scale well in the sense that if you have more information and less time, then this strategy, you might not be able to get to the right answer. So this distinction between parallel processing and serial processing has been studied and debated in the literature to exhaustion. And the main debate here is that whether you can actually conclude that someone is doing a serial process or a parallel process just based on how their behavior, just based on the decisions they make, their performance in different time constraints and different amount of information. So we decided to test this using MEG. So instead of looking just at the behavior, looking at the neural signals that and decoding these neural signals to figure out what people are thinking of at any given moment in time as they are making their calculations. So we had 40 subjects do this experiment in the scanner, and on each trial they saw one of these teams. They had 1 or 2 seconds to deliberate, and then they had to report how many goals the team will score. Looking at how, first of all, the decisions that people make, you can see that most people made their decisions were a bit more accurate when they had 2 seconds to deliberate as opposed to 1 second. But this was not true for everyone. So there was quite substantial individual differences in this regard. And then we also varied the amount of information, the number of player types that the team involved. So there were very simple problems involving only 1 player type, and these were relatively easy to solve. So people were quite accurate on these problems. And there were problems that were very complex with 4 player types, and people were much less accurate about this. But importantly, we see striking individual differences in this, where some people go from almost perfect to chance performance, and other people are not that affected by the complexity of the problem. Now, so we can quantify this sensitivity to time and sensitivity to complexity for each subject, and we found that these 2 types of sensitivities are actually very strongly correlated. And elaborate computational modeling of the decisions that people made revealed that these 2 types of sensitivities reflect, to a certain extent, an underlying dimension of individual differences, where that determines to what degree the resources, constraints, time, and information affect the precision of the calculation that people make. All right, so now looking at the neural data to figure out whether is it true that people with high sensitivity to time and complexity are doing the serial strategy, and people with low sensitivity are not doing the serial strategy or doing the parallel strategy. So to test that, we decoded the representations of each of the players from the spatial pattern of the MEG signal. So here I'm just showing you that it was possible to decode very robustly which players appeared in the team on each particular trial from subjects' neural data, and that was true for both groups of subjects. But then the important question is, can we see these sequences of players, right? So to test that, we measured the cross-correlation between the time courses of the representations of each pair of players. If the players don't appear one after the other, then we're going to get a symmetric cross-correlation function like you see here. But if they do, if there is some sequential relationship, then the cross-correlation function is not going to be symmetric, and we can measure this asymmetry, and it gives us an indication of sequenceness. So measuring the sequenceness for the two groups of subjects, we can see that only the subjects with a high sensitivity to time and complexity showed significant sequences of players coming one after the other, whereas we didn't see that at all in the group that had low sensitivity to time and complexity. So this supports the idea that serial processing indeed increases sensitivity to complexity and sensitivity to time, and we were able to show that for the first time by looking at what people are actually processing from moment to moment. There are other interesting results from this study. In particular, we could use this same sequenceness measure to see when the representations of the players is transformed sequentially into the representation of the decision that people arrive at. So we can pinpoint when during the deliberation time people made their decision, and that was another factor that influenced people's sensitivity to the amount of available time. Another thing that we looked at was the evolution of the internal evolution of the representation of each player in isolation. And it turned out that some people represented players more in a more efficient way. And that kind of representation contributed to low sensitivity to complexity. So if you're interested in hearing more details about these analyses, I'm happy to talk to you offline. So these are the people that contributed to this work, and thank you for listening.